Thank you very much for the invitation, the opportunity to be here, and for the nice introduction. So, as Andy was saying, I've worked on these subjects for a long time, let's say maybe 15 years or so. My background is in gravity and cosmology, more traditional cosmology, let's say, and some 15 years ago, I got interested in trying to apply some high energy theory tools to hydrodynamics, and as we will see, cosmology is a natural extension. Some aspects of cosmology are a natural extension of that. So along the years, I've collected many collaborators. I thank them all. I'm sure I'm forgetting someone, and I apologize if they'll see the video. And I will talk about our own work. As Andy was saying, many other people have contributed to the subject over the years, and I will not have time to cover what they have done. In fact, I will only have time to cover part of what I have done. So let me start by motivating why effective field theory is a good idea in a number of situations. And the story starts with symmetries. So we all know that symmetries are important in physics. And effective field theory is, in a sense, the attempt to squeeze as much juice as possible from out of symmetries. Okay, and in particular, there are well, we all know what a symmetry is. It's a transformation of the variables that describe the dynamics of a physical system, under which the dynamics are invariant. So the laws of physics are invariant under certain transformations. We call those transformations symmetries. There are a number of interesting symmetries. I will focus only on continuous symmetries because even though discrete symmetries are important in many applications, I want to use two aspects that are associated with continuous symmetries that are very important for me. And they're both called theorems. One is Noether theorem, and the other is Goldstone theorem. So I'm sure that most of you are familiar with Noether theorem, but maybe not all of you are familiar with Goldstone theorem. So I will review both of them. Noether theorem, by the way, by continuous symmetries, I mean a symmetry that depends on one or more continuous parameters, and those parameters can be made infinitesimal in particular. And when they go to zero, those parameters, we get a trivial transformation, we get the identity. So continuous symmetry is a transformation that is continuously connected to the identity. So when we have continuous symmetries, we have conservation laws, according to Noether theorem. This is true at the level of classical mechanics, classical field theory, quantum mechanics, quantum field theory is a very general theorem. The arrows go both ways. Whenever you have a continuous symmetry, you can find conserved quantities. Whenever you have conserved quantities, you can use them through Poisson brackets in classical mechanics or commutators in quantum theories to define transformations that are symmetries. And so we all know that associated with time translational symmetry, we have energy conservation. Associated with spatial translational symmetry, we have momentum conservation. Associated with rotations, we have angular momentum conservation, and so on. Every new continuous symmetry you can come up with, there is a non-trivial conservation law. The Goldstone theorem is also important for what I will talk about. And again, it's a theorem in quantum field theory, but in practice, one can extend it to a number of different situations, in particular classical mechanics, if one wants to, and I will show you an example later. So the theorem says that if a continuous symmetry is broken by the state of the system, so the dynamics are invariant, but the system chooses a state that breaks the symmetry. Classical example is the chair. The chair is not invariant under translations, even though it's kept together by Maxwell's equations, which are, it's not invariant under rotations, the chair, even though it's kept together by Maxwell's equations which are invariant under rotations. So the state of the chair breaks rotations. So whenever that happens, you have gapless excitations. And gapless in the case of classical systems means zero frequency, so there is no frequency gap. There is a continuum, if you want, of solutions that are connected all the way to the trivial solution by frequency going to zero. And in a quantum mechanical setup, it means zero energy. That is to say, they are degenerate with the ground state or the state that you are considering. And another important aspect of the Goldstone theorem, which usually is not part of the theorem how it's phrased, but it follows from the algebra, is that not only the theorem predicts the gapless excitations, but it also predicts that these gapless excitations, which go under the name of Goldstones, it also predicts the dynamics of these Goldstones, in particular, what terms one can write down in the Lagrangian or in the Hamiltonian of the system, not only at the quadratic level, but also including interactions or nonlinearities. So let me give you an example just to set the stage. So consider a long string, like a guitar string, okay, with some tension. The state of the ground state of the string, so a straight string, let's say, along the z direction, breaks a number of symmetries, okay? It breaks translations along the orthogonal direction because it's here and not here. So certainly the state of the string is not invariant under translations along the x direction. It also breaks rotations in the zx plane. If I rotate the string, I get a different looking string. And it also breaks Galilean boosts. Okay? If I boost the string along x, I get a movie string rather than a string at rest. So the Goldstone theorem tells us that there are gapless excitations, and these are nothing but the perturbations of the shape of the string from straight to, let's say, wave-like, that I can parameterize by a field, delta x, that depends on the z-coordinate and on time. Okay? These will be the gapless excitations. Gapless when the wavelength of these perturbations goes to infinity. So the theorem will say, in the long wavelength limit, the energy or the frequency of these excitations becomes smaller and smaller. Now, these symmetries that are broken by the string act non-trivially, quite non-trivially, on delta x. Okay? So one is a shift that depends on time, and one is a shift that depends on z. So you see that now, if I have to write down dynamics that are invariant under these symmetries, those dynamics will be pretty constrained. And I prefer to work with Lagrangians or actions. One could work with Hamiltonians. But certainly either one, I think from my viewpoint, are better than equations of motion because they are, first of all, more economical. There is a single quantity like the Lagrangian or the Hamiltonian, for all the degrees of freedom, and then by, I don't know, applying the variational principle, you can derive all the equations of motion that you need. This quantity can also give you conservation laws through another theorem, whereas it's very difficult to find a general procedure to get conservation laws from equations of motion. And moreover, you can quantize the system if you have the Lagrangian of the Hamiltonian, whereas it's not obvious how to quantize a system just from the equations of motion. So bottom line, I want to write down a Lagrangian for delta x that is invariant under all these symmetries. And after trial and error, you discover that the Lagrangian has to start like this. So there is going to be a kinetic energy proportional to delta x dot square with a generic coefficient in front, which it will turn out to be associated with the mass density along the string. And there's going to be this complicated square root structure, which is nothing but the invariant length of the string as measured along the curve defined by delta x. Okay? And the coefficient in front, which is an arbitrary coefficient, will turn out to be the tension. Plus dot dot dot. These will be finite size terms that take into account the fact that any realistic string will not be infinitesimally thin, but it will have a thickness. And I will tell you later how to take that into account. But for now, at the level of the infinitesimally thin string, these are the only two terms you can write down compatible with all the symmetries. And then you can find the equations of motion and linearize, if you want, for small perturbation for small delta x, the square root, you can take just the Taylor expansion of the square root. Equations of motion will tell you that this is the dispersion relation for the waves. You recognize what you learn in your first mechanics class, that the transverse excitations of the string has a have a frequency that goes like k times this quantity, which is nothing but the speed of the propagation square. The propagation speed of the excitations square. And all nonlinearities that you get from this square root will correspond to interactions between these waves. If you have two waves colliding, let's say along the string, their interaction are described as nonlinearities. So you see, with just insisting on symmetries, without ever talking about forces, for instance, we never use Newton's equations. Without ever talking about forces, we wrote down an action that gives you not only what you already knew about guitar strings, but also all the interactions that these waves could have. So this is an example of an effective theory for the Goldstone. The Goldstone excitation here is delta x, and this is the effective theory that you get by insisting on symmetries and organizing, as we will see in a second, everything in terms of derivatives, how many derivatives act on each term. These finite size effects that I omitted involve more derivatives. So here's the general recipe for effective field theories, and I will not prove anything, I will just state it, okay? An effective field theory for a physical system focuses on the long distance and low energy or low frequency dynamics. And in order to write down the action or the Hamiltonian, sorry, I need some water. In order to write down the action or the Hamiltonian of the system at low energies, you want to be able to isolate what the light degrees of freedom are. Here by light, I mean low energy in a quantum setup or low frequency in a classical setup. And if you know what they are, you use them. If you don't know what they are, you postulate what they are, and then you check whether what you get makes sense or not, either experimentally or if you have other ways to check from other aspects of the theory, you can check. And then you want to know, and this is an important part because otherwise there's too much freedom in writing down Lagrangians or Hamiltonians. You want to have a good set of symmetries. You want to have enough symmetries that constrain the terms that you can write down in the Lagrangian or the Hamiltonian. And these symmetries I generically denote like this. These are functional, so if I have some fields phi, the symmetry could send phi into some given functions of the fields. This could be linear transformations or nonlinear transformations, okay? For instance, in the case of the pion, these are nonlinear transformations. Here's a pion, okay? A pion is a complicated bound state in QCD, quantum chromodynamics. QCD is a strongly coupled theory. We don't know how to solve it analytically. In particular, we certainly don't know how to solve for the structure of the pion, which is the simplest bound state we have in QCD. However, it so happens that at long wavelengths, okay, because of the Goldstone theorem, the pion is supposed to be the Goldstone boson associated with spontaneously broken chiral symmetry in QCD. And so, first of all, we know it exists. In fact, there's 3 of them. We know that there are 3 Goldstone bosons, so we know that there exist light excitations, in this case the pions. And also we know that at long wavelengths they are weakly coupled with each other. And so we know how the symmetries that are broken and unbroken in QCD act on the pions, okay? And so we know, even though we are not even able to solve for the, if you want, the wave function of this bound state, we know that if we start scattering pions at very low energies, we know how to write down an effective Lagrangian that describes their interactions. And now you see the importance of organizing things in number of derivatives, because since effective theories are supposed to work at low energies or at low frequencies and long distances, and since, at least in a quantum theory, long distances and low energies correspond to small derivatives, okay? The fewer derivatives you have in a Lagrangian term or in a Hamiltonian term, the more important that term will be at low energies and at long distances. And so you want to organize your Lagrangian as a sum of potentially infinitely many terms, but organized in terms of the number of derivatives that appear, okay? compared to some UV scale, some microscopic scale, and some microscopic time, which I call LUV, and some microscopic frequency omega UV. And so the fewer derivatives you have in Lagrangian term, the more important the term will be at low frequencies and long distances. And so even though these effective Lagrangians have formally infinitely many terms, in practice, at any finite order in this expansion, only a few of them will matter. And so it has proven to be an extremely powerful tool in particle physics, and it's because the dynamics that you can write down in these ways are extremely constrained by symmetry. And what I want to talk about today is applications of these ideas to condensed matter, broadly defined. Okay, I want to talk about condensed matter as systems that break certain space-time symmetries. In particular, they choose a rest frame, so they certainly break relativity, either Galilean or Lorentz, but that are still approximately homogeneous, at least at large distances. For instance, a solid, even if it's a crystal, let's say, at the microscopic distances, it is discrete, but at very long distances, you can replace it with a continuum, and it becomes approximately homogeneous, and we can write down field theories for that. And you see now the connection. Cosmology, if you want, which is the dynamics of the universe on very large scale, is nothing but a condensed matter system, broadly defined, let's say a fluid of galaxies, for example, now, coupled to gravity. So if we have a field theory description in this language, purely based on symmetries of condensed matter systems broadly defined, and we couple it to gravity, we get cosmology for free, if you want. And I want to show this picture. So this is, as many of you know, this is a picture of the cosmic microwave background radiation, which is a snapshot of the universe when it was 400,000 years old, which is much younger than today. And so this is the oldest picture that we have of the universe, if you want. And the anisotropies that you see here, they are greatly exaggerated. The actual fluctuations in temperature of the cosmic microwave background from cold spots to hot spots are 10 to the minus 5 compared to the background temperature. So this tells us that if we have a field theory that will lead us to make predictions about this map, well, that field theory will be weakly coupled, at least at the scales of interest, at the scales that we can see in this map, because the fluctuations are of order 10 to the minus 5 compared to the background. So we will have a perturbative description, a field theory perturbative description of the very early universe, or at least of those fluctuations. So let me start with the first non-trivial example. I will just give you a few examples, okay? I will not give you the whole general theory because it will not be useful use of time. So let me start with the example of hydrodynamics. So hydrodynamics is perhaps one of the most, one of the oldest example of an effective theory. And usually it's done at the level of the equations of motion, and I want to do it at the level of field theory, if you want, at the level of an action for a field theory. So why is hydrodynamics a field an effective theory? Well, let's think about, for instance, a weakly coupled gas. In a weakly coupled gas, we have molecules or atoms going around. They're essentially free. Every now and then, they collide with each other, but let's say the collisions are very rare. However, as soon as there are interactions, however small, there's always a critical length scale, let me call it L, above which you cannot ignore interactions anymore. That is defined to be the mean free path. It's the distance on average that you have to travel before you bang into another particle with probability of order 1. So by definition, after that distance, you have almost surely collided with another particle. So above the mean free path, there is no way to neglect interactions, even in a very weakly coupled gas. On the other hand, we know that there is a new effective description that is valid at much longer wavelengths, and that is exactly what hydrodynamics is about. Hydrodynamics is the effective theory of perturbations of a thermal system that have wavelengths much longer than the mean free path and frequencies much smaller than the inverse mean free time. Okay? And we know from experience with hydrodynamics that at those very long wavelengths, it's pretty useless to think about the microscopic details of what the gas is made up of. It's much more useful to think in terms of collective degrees of freedom, like sound waves and vortices. Okay, those are the degrees of freedom of hydrodynamics. So how do we write down a field theory for hydrodynamics? And I'm only doing perfect fluid, okay? There is a vast literature by now, which started maybe some 10 years ago, initiated by Hong Liu and collaborator, about how to include dissipation in this formalism, and it's very useful, but it's also quite complicated, so I don't want to say anything about it, okay? I'm only just giving you the example of perfect fluid effective field theories. What is a perfect fluid? It's a fluid without viscosity. It so happens that in hydrodynamics, those of you who have seen the Navier-Stokes equation a few times, the longer the wavelengths that you use, the less important viscosity is. So from the viewpoint of the first effective theory that I gave you, the effective theory of the string, viscosity is a finite size effect. Viscosity has one more derivative compared to perfect fluid hydrodynamics, and that derivative is suppressed by this scale, the mean free path, which from the viewpoint of this long perturbation is a microscopic scale. So if you want all fluids at very long wavelengths become more and more perfect, in quotes. Okay, so how do I talk about a perfect fluid in effective field theory terms? Well, think about a fluid or a generic medium, even a continuous solid, like a jelly, let's say, as some blob, okay? And the blob can move in space, it can get deformed. And so if I erect a coordinate system, a curvilinear coordinate system that lives inside this blob, and it moves with the blob, and it gets deformed with the blob, and I call these comoving coordinates, let's say phi1, phi2, and phi3, then the configuration space of the medium is completely determined if at any point and at any time I give you the local value of phi. What I mean is this quantity, these fields, phi1, phi2, and phi3, tell you the comoving coordinates of the volume element that is going through position x at time t. X is your fixed lab frame, and the phi i's are coordinates that live in the medium. The configuration space is completely given by the mapping between these two coordinate systems. Okay? This is true for solids and fluids. And of course, you want to choose coordinates wisely so that at equilibrium, let's say at some given pressure, external pressure, the comoving coordinates and the physical coordinates are aligned with each other. So that's the simplest configuration. So this will be your equilibrium configuration. Okay, this is, if you want, defines your choice of coordinates. You choose coordinates such as at equilibrium, they are nothing but the lab coordinates. And then you have to figure out the symmetries. So these were the degrees of freedom, and now we have to figure out the symmetries. I'm doing everything relativistic for now, simply because I find it simpler. You could redo the same analysis for Galilean invariant systems rather than Poincaré invariant system. I'm doing everything relativistic. So I want to impose the Poincaré symmetries, which are translations and Lorentz transformations. And because those are fundamental symmetries of physics, so those must be there. And then, and notice, by the way, you could say, well, but a fluid, of course, breaks Lorentz transformations because it chooses a reference frames. But that's a spontaneous form of breaking. It's the state of the system that breaks the Lorentz transformations. It's not the dynamics. So that's the difference between having a symmetry and in the dynamics or not. And then I want to impose certain internal transformations and the way on the fields. And the reason I want to do that is because this equilibrium configuration that describes a fluid at rest in a homogeneous and isotropic state, formally, since I have some scalar fields that depend on x, non-trivially, formally this breaks translations and rotations. But I want this system to be invariant under translations and rotations. I want it to be homogeneous and isotropic. So the only way out we found, maybe there are others, is to impose that on your fields there are certain internal symmetries, like shift symmetries acting on your fields, and rotations acting on the fields, such that this configuration, although it breaks shifts and spatial translations, it preserves the diagonal combination of shifts and spatial translations. If you perform a shift of phi and a shift of x, this configuration is invariant. Likewise for rotations, if you perform a rotation of phi and a rotation of x, this configuration is invariant. So these symmetries will constrain the actions that we can write down. And then there is a final symmetry that distinguishes a fluid from a solid. What is the difference in the continuum limit? What is the difference between a fluid and a solid? Is that in a fluid, if you adiabatically move things around without compressing or dilating the fluid anywhere, you don't pay any energy price, okay? Whereas if you try to do that with the solid, you feel very strong transverse stresses that want to bring the solid to its ground state. So there is a big degeneracy in the fluid of ground states, if you want, or to use this term. So you can move things around adiabatically slow and you don't pay any energy price. So at the level of this field theory, this is implemented by a volume-preserving change of these internal coordinates phi I. If you change your coordinates phi I by any function of them, as long as the Jacobian is 1 everywhere, so as long as you do not compress or dilate the fluid anywhere, you don't pay any energy price. So with all these symmetries, the action that you can write down is very constrained, okay? It must be a generic function, that I will explain to you in a second what it is, of this particular invariant. The square root is there for convenience, okay? So just look at this determinant. So you have to use derivatives of phi because of the shift symmetry. Phi itself is not invariant, but if I act on it with a derivative, this constant goes away, so the derivative of phi is invariant under shifts. And then I have to contract the derivatives because of Lorentz symmetry. Otherwise, I have a mu index there that I don't know what to do with it, so I have to contract it with another mu index. So the building block is this matrix d mu phi I, d mu phi j. It's a matrix in ij space. And now I have to write down a function of that matrix that is invariant under these internal rotations and, more importantly, under these volume-preserving changes of coordinates. And the only invariant that you can have is the determinant, because the determinant of this combination will change under volume-preserving changes under changes of coordinates by the determinant of the Jacobian. But the determinant of the Jacobian that we are using is 1. So this is invariant, so it's the square root. So the action to lowest ordering derivatives is a generic function of this invariant. This action, this generic function happens to be related to the equation of state, okay? In particular, you can check that if from this action you derive the stress energy tensor and the equations of motion, you get exactly what you expect for hydrodynamics with the following identifications: that the energy density should be this function itself, the pressure should be this combination of this function and this derivative, and u mu, the four-velocity field of fluid motion, is a particular combination of your scalar field derivatives, okay? This is not really relevant. But now you see that if the equation of motion, if the equation of state is a relationship between rho and p, then if you impose that relationship, this is a differential equation for f. First order differential equation for f that you can solve. So for each equation of state, you have an f. For each f, you have an equation of state. So this f is completely determined by the equation of state. And this action, which, as you can see, is a very simple, it has a very simple structure. It's a single function of a single variable. Is fully relativistic. It's fully nonlinear. So it reproduces completely relativistic nonlinear hydrodynamics. If you want, if you're dealing with a non-relativistic fluid, you can take the non-relativistic limit in the usual way by focusing on small velocities compared to c. Remember our ground state at some given p was this, and now you can consider small perturbations. So there's many broken symmetries here, okay? There are the boosts, the Lorentz boosts, there are those rotations and those shifts acting on phi I. Those are all broken by the ground state, as we said. And the Goldstone bosons, the Goldstone excitations associated with those symmetries are simply displacements of these fields from their equilibrium configuration. Let's call them pi I. You can expand the Lagrangian in small perturbations about that ground state, and you get a quadratic Lagrangian of this form. There are nonlinear terms which are interactions. Let me forget about them. You get a kinetic energy for all the pi fields, and you get gradient energies only for the longitudinal pi fields. With here, this coefficient is the usual speed of sound. It happens to be the derivative of p with respect to the density, which is the usual expression for the speed of sound. And so you can look at the equations of motion for this quadratic Lagrangian, and they are linear equations of motion. And the longitudinal pi's obey this dispersion relation, and these are identified with the sound waves. And the transverse pi's obey this equation of motion, which is the lowest order equation of motion that you have for vortices. If you think of a vortex in constant rotation, okay, you can make, there is no relationship between how small or big that vortex is and the velocity at which you can make it rotate. We can make a vortex rotate arbitrarily slowly. At the linearized level, of course, a vortex is a very nonlinear solution, but at the linearized level, this statement corresponds to zero frequency for transverse modes. And there's been many applications over the years of this formalism. Some applications by me and by group, other applications by other people. Perhaps most importantly, as we said, the work of Von Liu and collaborators on dissipative hydrodynamics. And they unfortunately won't have time to show you many examples of these applications. But let me just focus on one particular example, which I find particularly nice. It's the dynamic of vortices. And to motivate why I want to talk about some specific forms of vortices, let me talk for a second about the difference between a superfluid and a perfect fluid. Okay? So usually we say a superfluid is a fluid with zero viscosity, but we are already in the limit of zero viscosity when we talk about perfect fluid. So is there any difference between a superfluid and a perfect fluid? So there's an important difference. So from the viewpoint of the compressional modes, so the sound waves sector, both systems obey the same hydrodynamical equations. They are exactly the same. But they have very different transverse modes. They have a very different vortex sectors. In a ordinary fluid, as I told you, you can make arbitrarily slow vortices if you want. First of all, you can make them as big as you want in terms of gradients. You can have very mild gradients for your vortices. Look at the hurricane. It has, I don't know, gradients of inverse kilometers, I guess. And also you can make them rotate arbitrarily slowly if you want, okay? Whereas in a superfluid, in the bulk of the superfluid, the vorticity, which is the curl of velocity, must be zero. That's one of the defining features of superfluid flow. Which means that if you do have a vortex, it must be singular, okay? All the vorticity is localized on a line, which realistically, let's say in liquid helium, is of atomic size, okay? So it's as big as an atom, okay? And then the velocity rotates around it like this. So these are two very different vortex sectors, okay? Now, it so happens that in a fluid you have a lot of freedom to build up vortex solutions. And so in particular, you can also approximate these idealized vortex line solutions. And the nice thing about these vortex lines is that instead of having to, if you want to talk about vortex dynamics, if they evolve in time non-trivially, instead of keeping track of a full three-dimensional map of the velocity field, you can just think about where the line is going. And where the line is going will determine then the velocity flow around it. So even for a normal fluid, it's useful to focus on solutions that are line-like. Those are called vortex lines. And so let's look at the dynamics of vortex lines. And for simplicity, let me take the incompressible limit. The incompressible limit is defined by having a velocity with zero divergence. So you cannot compress or dilate, which means that things cannot accumulate or get out of a source. So the divergence of the velocity has to be zero. And so the whole fluid flow is defined by the vorticity, which is the curl of the velocity. And now you see that we can think about a magnetostatic analogy. Another field that we know that has a zero divergence is a magnetic field in magnetostatics. And in that case, if we identify V with some fictitious magnetic field, omega is some fictitious current density. And so on a vortex line, okay, the current density, this analog current density will be localized on a line. So it's actually a current flowing in a wire, if you want. So you can think of a vortex line as a current carrying wire. And that current I is defined by the so-called circulation, which is the integral of the velocity around the line. Because if the velocity is the magnetic field, indeed, the magnetic field around the line is a circulation. This is an analogy, okay? I'm not talking about real magnetic fields. This is an analogy. So in this case, the circulation is identified with the current, and the velocity is identified with the magnetic field. Why is this useful? Because we know how to write down directly the velocity field through the Biot-Savart law. There is the current, and then there is this Biot-Savart integral that normally would define the magnetic field around the wire, and now it defines completely the velocity field in the whole fluid as soon as you have a vortex line of a given shape. You see, this integral is just a function of the shape of the vortex line. Not only that, but you can prove, if you look at the equations of motion of the fluid, that the extrapolation of this velocity field close to the line is the velocity with which that line element itself moves. Okay? So the extrapolation of this field V of x to the line is the velocity of the line itself. Why is this interesting? Because then you can interpret this as an equation of motion for the line that is completely determined by the geometry of the line. I give you a line, and you know what the instantaneous velocity at each point on the line will be. So it's a first-order equation of motion, because the velocity is a single time derivative of the position of the line. Why is this interesting? Because it's totally unlike mechanics. There is no F equal ma here. Okay? The equation of motion is not acceleration equals something. It's velocity equals something. So there's no room for forces. For instance, if I ask you, okay, how does this change if I add the gravitational field? I don't know, because I cannot add the gravitational force to the right-hand side. It's not of the right form. And also, which is another way to say that the instantaneous velocity is completely determined by the geometry, so not even the acceleration, just the velocity directly. And there's no initial condition for the velocity. I cannot tell you, suppose that I have a vortex line moving at this velocity. No, it's not up to me to tell you what the initial velocity is. The system decides what the velocity is. And related to this, if you look at a straight line and you consider small perturbations, these are called Kelvin waves. They were found by Kelvin in 1880. And there's two modes overall. Again, a consequence of single time derivative equations of motion. You don't have two polarizations for waves going up and two polarizations for wave going down, like I would have, let's say, in a guitar string. Okay, I can make a guitar string vibrate, a line like this vibrate like this, or like that. Here, there's only one polarization going up, one polarization going down. They're both circular polarizations, and they have this funny dispersion relation. Omega, going up or down, goes like the wave number square times this logarithmic term, where A is of order of the thickness of the string. By the way, of course, Lord Kelvin did not do this for superfluids, okay? He did it for normal fluids. But again, these solutions, these approximate solutions, if you want, also exist in normal fluids, so you can find them. And it's quite difficult to find these solutions, and in particular these dispersion relations, from hydrodynamical equations. And moreover, this logarithmic term, that is the log of a wave number, if you want, should raise some concerns. Usually, things that are not analytic in wave number, when wave number goes to 0, that is to say, they're not simple power of wave number, but they have either square roots or logarithm of the wave number, come from some sort of non-local equations of motion, and usually they mean that we have, in the particle physics language, you have integrated out some gapless degrees of freedom. That is to say, we are not keeping track of all the degrees of freedom here, which in a sense we know that we are not, because here we are parameterizing everything just in terms of the shape of this line. But we have sort of forgotten about the fact that there is a whole fluid around it, and those also has gapless degrees of freedom. And as we will see, there's a very simple way in our language, in the language of effective theories, to see the emergence of this non-local term coming from the bulk of the fluid. And related to this, if you now take one of the vortex lines and you join the ends, there's also vortex ring solutions. So there are rings with the circulations going around like this. And they also move, they also obey first order equations of motion. They move at a velocity that is completely determined by their radius in this way. Okay? Again, using the magnetostatics analogy, the velocity field far away is the same as the magnetic field of a dipole with this particular dipole moment. So you can actually do experiments on these things. So this is William Irvine at U Chicago. He has a lab in which he studies, or at least he used to study. I don't know what he's doing now. These videos are like 10 years old. He studies vortex rings in water. So what you will see is this. So these are 4 videos. I will play them in succession, so in sequence. So in this video, there is water being pushed out of this hole. And you see these white things. These are tiny air bubbles. And it so happens that for vortex lines and vortex rings, the pressure is lowest at the core of the line or at the core of the ring. So those air bubbles will float, in quotes, to the core. So those air bubbles are used as tracers for vortex lines and vortex rings, okay? And so the first video is a very simple vortex ring being formed by pushing water out of that hole. You see that the air bubbles slowly float to the core. By the way, these are not simulations, these are data. These are 3-dimensional data. And in fact, they have a very fast tomographic technique, so that these are fully 3-dimensional videos that they can rotate at any time. In fact, some of these videos will be rotated. So in these other cases, instead, there are these shapes. These shapes are plastic things made with a 3D printer. And the shape is not particularly well designed. As far as I can tell, they just found them by trial and error. I mean, they tried many different shapes, and some work, some don't. And these shapes are going to be pulled very quickly down, and they will leave behind some fluid flow. And again, there will be air bubbles floating towards the core of whatever vortex lines and vortex rings are formed. So in this case, you see this shape is some sort of trifoil shape. And from the viewpoint of this, from the viewpoint of a circular ring, it's a perturbed singular ring. And you will see that there will be Kelvin waves that are circularly polarized. They will be very quickly out of plane. You see they go out of plane immediately. So those are circularly polarized Kelvin waves going around that ring. And these two are topologically non-trivial configurations. They're actual knots. And this group was the first one to produce knotted vortices. You see, this is knotted onto itself. It's kind of rough, but you can see it. And these are 2 rings knotted onto each other. Now, it so happens that there are other groups, by which I mean other groups of other groups of mammals that play with vortex rings, and in fact, they're much better than William Irvine. I don't know why, but so this particular species of dolphins, in fact, this is in a water park, I think in Orlando, Florida. They just push out water from their blowhole, and they create this vortex. So again, they push out air from the blowhole, and the air serves as a tracer for the vortex ring that gets formed. And they are mesmerizing and beautiful to watch, and they play with it, and you see they are able to bite off smaller ones, and you see, and they're edible apparently. And they live, you see, they're extremely long-lived excitations and very stable. You can just do that. They can do that. Probably because they live in water, so they have an intuition about how these things work. And they live for tens and tens of seconds. They are extremely long-lived objects. Anyway, so, wow, I'm almost out of time. So in the last, so I wanted to talk about many more things, but maybe I will come to the conclusions pretty soon. But at least let me tell you how to build the effective theory of these objects. Because again, their equations of motion are pretty useless, at least for me, because you don't know how to modify them. For instance, I told you that this is the equation of motion, but it's only valid in the incompressible limit. So if I now want to talk about compressibility, for instance, sound waves are compressional excitations in a fluid. So how do I talk about the interaction of these things with sound waves? I don't know how to do it from the level of the equations of motion, because since the equations of motion are not F equal ma, I don't know what to add. What are the rules of the game? But if I come up with an action based on symmetries, I know that whatever terms are compatible with the symmetries in an action should be there, and so I can start modifying it. So how do we do an effective field theory that reproduces this equation of motion? So the quick way would be trial and error. Okay? What is trial and error? Where I have some fields x that depend on time and on some parameter lambda. Lambda will be a coordinate along the string, the vortex line, and time is time. And this x tells you at any given time the position of the string at that value of lambda. Okay? And so I just discover, so by trial and error, you discover that this particular action, which includes this long-range interaction, because now I have a double integral over 2 copies, if you want, of the string, reproduces correctly this equation of motion. Okay? You can just write down the Euler-Lagrange equations or the variational principle. You discover that this action reproduces the equation of motion. Now, the electromagnetic, so the magnetostatic analogy comes in handy now, because this is a long-range interaction, which is also what we have in magnetostatics and electrostatics. And we know what the good idea is for electrostatic and magnetostatic, is to introduce local fields that are sourced by the sources, and on the other hand, interact with the sources. So you can rewrite this long-range interaction as a vector potential, like in magnetostatics, with its own gradient energy, and its own coupling to the current. In this particular case, remember, our current was a current going along the wire, and this is an integral going along the wire. So this is exactly the term you would write down in magnetostatics that tells you what the magnetic energy is and what its interactions with sources, with currents is. Okay? And so again, the analogy is that the current density J is the vorticity, the magnetic field is the velocity, and the vector potential of magnetostatics is a vector potential for a fluid which, for lack of a better term, we call the hydrophoton, because the photon is the field, is the particle for electromagnetic field, and we call this the hydrophoton. But you see, the analogy is very, very precise, apart from the fact that the way now the sources respond to this magnetic field is simpler than in magnetostatics. We don't have a Lorentz force. We have directly that the magnetic field is the velocity field of these sources. Now, the responsible way of doing effective theory is what I told you at the beginning. figure out what the degrees of freedom are and figure out what the symmetries are. Degrees of freedom are the position of the vortex line for a given value of the parameter that goes along the line and for time, at a given time. And then the velocity field in the bulk of the fluid, which is, since the velocity field is divergence-free in the incompressible limit, it must be the curl of something. Okay? And then you can figure out what the symmetries that act on these fields must be. You have translations and rotations that act on these fields in the obvious way. They translate x, and they translate the argument of A. We have reparametrization invariance along the string. Simply, you can choose any parameter to parameterize the string. Only, let's say, for instance, the physical length will be an invariant, but the parameter that you choose along the string doesn't matter. And then you have either, I'm now doing everything non-relativistic for simplicity, you can say that you have Galilei boosts, so Galilean transformations in which you choose a different reference frame, are spontaneously broken because your fluid has a preferred reference frame, but you can check that everything, that they are correctly implemented if you translate x in the obvious way, the velocity field in the obvious way, you shift the velocity field by a boost, and then this A should shift like this, simply because of this relationship. You want the V and A be related by this relationship, so this is consistent with Galilean invariance only if A shifts like this. And then you can write down the invariants. So the only terms that you can write down in the action to lowest ordering derivatives are these gradient energy for A, which is exactly the magnetic energy we wrote before, and this particular combination of derivatives of the X fields, including the coupling to the hydrophoton field, which is exactly what we wrote down. Sorry, what we wrote down. Oops. What we wrote down earlier. This is exactly what we wrote down earlier. This is invariant by itself, and the combination of this and this are invariant. So, as I said, there are many other things I wanted to talk about, but I went much slower than I predicted. Just as a fun side note, and then maybe we'll conclude. It's well known also for people who are, for instance, in quantum field theory, when people consider what we call cosmic strings. It's well known that if you have a string of this type, and you compute the energy, of course the energy is infinite if the string is infinitely long, but let's say the energy per unit length is still divergent. Okay, it's logarithmically divergent with the size of the container and the UV cutoff, the microscopic scale that determines the thickness of the string. Okay, in this way of doing things with this effective theory that I give you, you can compute the energy of the string simply by a Feynman diagram. Those of you who have seen quantum field theory for particle physics know very well what Feynman diagrams are. In this case, it's a self-energy diagram of the string exchanging this vector potential with which it interacts with itself. Okay, so you can compute in with a simple Feynman diagram what is the contribution to the energy of the string given by this self-interaction of the string with itself through this vector potential. And you get exactly the classic result that the energy per unit length diverges logarithmically. But now the difference is that since you have a Lagrangian and you know from quantum field theory know-how how to do renormalization, in particular how to take care of infinities that arise in quantum field theory, you know that you can reabsorb the UV divergence by adding what we call a counter term. So there must be a new term that you can write down, you can write in the action that absorbs the infinity, and you're left with something finite and observable. Okay? In particular, the counter term associated with this UV divergence is nothing but what we will call the normal tension of the string, that is an energy per unit length that simply in the Lagrangian multiplies the physical length of the string. And so if you do the standard renormalization procedure of quantum field theory, you end up with a renormalization group equation, for those of you who know what I'm talking about, for the tension itself. So now the tension of these strings runs with scale. What does it mean? It means that if I consider processes which has a typical length scale or a typical momentum scale, let's say if I consider the scattering of two strings, for instance, or if I consider excitations in a string of a given wavelength, the tension that I have to use for the string is going to be slightly different, okay? It's logarithmically different depending on the scale that I have to use. And this is the origin of the log, of the logarithm in the Kelvin waves that I told you about. In this language, the fact that Kelvin waves, so excitations on a string, have a logarithmic dependence on wave number comes from the fact that the tension for these strings, unlike for a guitar string, the tension for these strings is not a constant. It depends on the scale at which you probe it. Okay? And then I guess I will conclude here, even though I had a bunch of other things. Sorry. I was too ambitious. Okay, let me summarize. I didn't talk about cosmology at all, okay? But let me just summarize that I hope I gave you at least some sense for which I believe that, some sense in which I believe that, in particular, spontaneously broken symmetries and Goldstone excitations of effective field theories are very general concepts and very powerful tools. They are a language and they're a framework. They're not necessarily better than other languages or framework, but they're just different. So they invite new questions and they naturally generate new ideas if you approach systems thinking about them in these terms. And so they have many potential applications in condensed matter, broadly defined, and fluid dynamics and cosmology, which I didn't talk about, unfortunately. Thank you very much.
Maybe I can ask, this might be related to the cosmology thing.
Yeah.
That you get to, but if you, I guess if I, like one thing I might worry about is if I try to couple hydrodynamics to, let's say, the Einstein field equation, but there's some mismatch derivative, sort of like in, yeah. So I'm not sure if this makes sense, but like the Ricci tensor has two derivatives in it, and I'm mapping it to stress tensor ideal. I guess does the effective field theory give you some way to sort of do this maybe more systematically without, or is it sort of necessary to introduce some length scale?
Well, there will be an hierarchy. I don't know if this answers your question, but there will be an hierarchy of scales. So, let's think about, for example, a weakly coupled gas. Now, we said that hydrodynamics is a good description at wavelengths much bigger than the mean free path. Okay, so whereas you know that so this, if you want, this scale controls the strength of interactions in hydrodynamics, and it controls what suppresses derivatives in the hydrodynamic effective theory. Okay, so the hydrodynamic effective theory will be controlled by these powers of this. Okay, now gravitational interaction, as long as this mean free path is much bigger than the Planck scale, gravitational interactions will be much weaker than this.